Imagine a blindfolded chef trying to perfect a new soup recipe. They taste, guess the missing ingredients, have a judge score the outcome, and tweak the recipe. A neural network learns using this same continuous loop of trial, error, and correction. This diagram shows a computational neuron. To predict an exam score, we feed it inputs, like ours studied. Inside, it calculates a weighted sum, z equals w times x plus b. Weights decide input importance, while bias provides a baseline. This graph shows a ReLU activation function. Without an activation function like this, our neuron would only be able to draw flat, linear relationships. ReLU takes our weighted sum and flattens any negative number to 0. This creates a non-linear threshold, allowing the network to map the complex realities of actual data. On its own, a single neuron is just a tiny calculator making a binary decision. Real intelligence requires stacking thousands of these basic decisions together. This image outlines a multi-layer neural network. An input layer receives data, hidden layers process features, and an output layer delivers the prediction. Before training, we initialize connecting weights. If all weights start at 0, neurons perform identical math, paralyzing the network. When we push our first batch of data through these randomly initialized layers, the network generates a final prediction, mathematically represented as y hat. We call this entire left-to-right journey the forward pass. Because the initial weights were random, this forward pass is a sophisticated guess. It has no value until we measure exactly how wrong it is. We measure that error using a mathematical ruler called cross-entropy loss. It takes our prediction, compares it to the actual truth, and produces a single number. A high loss means our weights are wrong. A low loss means our weights are accurate. To minimize loss, the network acts like a hiker finding the steepest downward slope. This is gradient descent. Updating weights after every data point creates a jagged path. Instead, calculating error over a mini-batch averages out noise, creating a smooth path down. Knowing how to step downhill is simple, but calculating the exact slope for a single specific weight buried 3 layers deep requires a different mathematical engine. With backpropagation, we pass the final error backward through the computation graph. At each node, we multiply the arriving upstream gradient by the internal local gradient. If an addition node's upstream gradient is 5 and local gradient is 1, what is the downstream gradient? The answer is 5. By multiplying 5 by 1, we successfully chain the error backward. This continuous cycle of backward multiplication is the actual mechanism of learning in machine learning. The weights and biases adjusted during backpropagation are the network's parameters. But the human designer also sets fixed rules for the training environment, like the learning rate or the batch size. We call these settings hyperparameters. Momentum acts as an optimizer. If our hiker hits a shallow ditch on the hill, momentum provides the energy to roll out and keep descending. Nesterov momentum looks ahead at the slope, applying brakes so the ball doesn't roll past the true bottom of the canyon. If a network is too dense, it memorizes training data rather than learning general patterns. We prevent this using dropout. By randomly turning off a percentage of neurons during training, we force the network to route signals through alternative pathways, ensuring robust learning. Hyperparameters are human guardrails keeping the mathematical learning process stable and generalizable to the real world. Let's put it all together. We initialize parameters, push a mini-batch through the layers for a prediction, the forward pass. We calculate loss and apply the chain rule backward, backpropagation. Finally, we use dropout and momentum to adjust weights, gradient descent. This image is a reference layout of the entire life cycle. Take a screenshot here. On the left are the core formulas, and on the right is exactly what they mean in plain English. Stripped of the jargon, a neural network functions as an automated mathematical cycle of trial, error, and correction.